Hi everyone, I'm really excited to be here today presenting on one of my favorite topics of self-programming artificial intelligence. I wanted to start this presentation off with a simple question. Is it possible for a computer program to write its own computer programs? Now, before I get started, I just want to give a quick introduction of myself. My name is Kory Becker. I'm a software engineer at Bloomberg. I am a web application developer where I develop web applications and web services, although my core interest in computing has always been artificial intelligence and machine learning. I'm also the author of the book, Building Voice-Enabled Apps with Alexa, published in 2017 by Bleeding Edge Press. This is actually one of my first published books. I can't believe it's already been that long already. The book is really interesting as it talks all about how to create software for the Amazon Echo and the Amazon Alexa service. So is everyone familiar with the Amazon Echo? It's a device that you can talk to and it executes a series of actions based upon voice commands. So the book is actually very interesting as it talks all about not just how to create software for the Echo, but also the history of chatbots and conversational UI, starting from one of the earliest examples of chatbot technology, which was Eliza the chatbot. So Eliza was developed in the 1960s as a psychoanalyst program, and it's really fascinating as it's one of the first examples of a chatbot where people actually believe they were talking to another human being instead of a computer program. So it's incredible how far we've come today, all the way from the 1960s to today with chatbot technology, and to compare and contrast the two. Now, to start this off, I do consider myself an AI enthusiast. I've always been fascinated with the idea of artificial intelligence, especially the idea of a computer program being able to create its own computer programs. Now, many of us in this room virtually are in the computer science industry or working as engineers or technology professionals. And you might be saying to yourself, well, gosh, if computer programs can write their own software, will that mean that I'll be out of a job in the near future? Well, that may or may not necessarily be the case, as we'll get to a little bit later in this presentation. So to start this off, one of the techniques that I've experimented with that has yielded some amazing results is with genetic algorithms. So I do like to clear up a little bit of media hype before I really dig into the genetic algorithms portion, just to talk about the branches of AI. So the media likes to say things like, chatbots are going to take over everyone's job. AI is going to take over the world. Now, not to belittle machine learning, but I do want to get across that AI is not exclusively equal to machine learning. There are so many other branches of AI that offer huge opportunities. Some of those include logical and symbolic AI. So examples of those are Shaky the robot. You can see in the upper right corner of this slide. Shaky the robot was developed by the Stanford Research Institute in the 1960s, and it's one of the first examples of a robot that could perceive and reason about its world and surroundings. So Shaky the robot actually used human readable representations of knowledge with logical and symbolic AI in order to execute a series of actions to complete a plan and achieve a goal. It was a very advanced implementation of artificial intelligence for its time. In addition to logical and symbolic AI, there's knowledge-based AI, there's common sense AI, pattern recognition, inference, AI planning, heuristics, ontology, artificial life using cellular automata, another fascinating area of artificial intelligence. And of course, the topic of this presentation is genetic algorithms and evolutionary computation. So what are genetic algorithms? Genetic algorithms are a branch of artificial intelligence that deal with simulating evolution among thousands of genomes to produce the best offspring, most fit to solve a particular task. So in the case of a self-programming AI, of course, that task is writing its own computer programs. Now, I like to compare this idea to the infinite monkey theorem. So the infinite monkey theorem states, has anyone heard of this theorem before? The infinite monkey theorem states that if you have 100 monkeys banging on 100 typewriters, given enough time, they'll eventually write out a complete work by Shakespeare. Now, I know this sounds crazy. How can monkeys possibly write an entire play by Shakespeare? However, consider just from the simplest scenario. Isn't it possible that given enough time, one of those monkeys on one of those typewriters will by accident end up hitting the first letter in the first word of the first sentence of a Shakespearean play. Certainly we could agree to that. So take it to the next level. Isn't it possible that at some point, given enough time, one of those monkeys will end up hitting 2 consecutive letters in the correct sequence of the first word of the first sentence in a Shakespearean play? So if we can agree on that as well, then extrapolating this idea to its final conclusion, given infinite time, surely it's possible that one of those monkeys will end up typing every consecutive letter in all of the words and all the sentences in a Shakespearean play. Now, of course, we don't have infinite time to wait. That would simply take too long. So what if we could speed up the process? What if we could give the monkeys a banana every time they type the correct sequence of letters in a word? Perhaps using a reward system, we could guide the monkeys into a more structured approach into achieving a solution in a much shorter duration of time. And this is exactly the idea behind program synthesis. So program synthesis is a more formal naming for self-programming AI. It's simply computer programs that can automatically generate their own computer programs for a specific goal. Now, since the beginnings of artificial intelligence, this problem has been considered by some to be the holy grail of computer science. Just imagine the capabilities that computers could achieve if they could write their own programs. Now, program synthesis can be done in several different ways, such as neural networks, deep learning, abstract syntax trees, programming by example, which is another fascinating area of program synthesis, and of course, genetic algorithms using evolutionary computation, which is what we're about to see right now. So in the case of using a genetic algorithm for self-programming AI, a programming language is required that's easy enough for the AI to manipulate. The selected programming language in this research is very difficult for humans to understand. It's very esoteric. However, it's very simple. And it's these qualities of this programming language that make it perfect to use by an AI. So it actually contains 3 key qualities. The first is that this programming language is Turing complete. So this is the most important one. A Turing complete programming language means that the language is theoretically capable of solving any computational problem in the universe. Now that's a bold statement. So by extension, an AI using a Turing-complete programming language can itself develop programs that are Turing-complete and capable, theoretically, of solving any computational problem in the universe. So with this quality, we've opened the door wide open to the range of programs that could be produced by the AI. The second key quality is that the programming language consists of just 8 instructions, 1 byte each. That's the set of program instructions right there in the slide. That's the entire programming language. It's quite incredible, just 8 instructions, and you have a Turing-complete programming language. Because you have such a limited instruction set, this leads to the third key quality, which is that it's very easy to build an interpreter for and to expand upon. This makes an ideal scenario where an environment where we can safely and carefully construct our AI to build and execute these generated programs without causing harm or damage to the system that it's running on or outside of the context of the simulated environment. We can also expand upon the programming language as we need to, since we're building our own interpreter for it with such a simple instruction set. Okay, so how do we generate a program? To generate a program, we first create a genome. So a genome is encoded as an array of doubles or floating point values. Each value corresponds to a programming instruction in a language. The genomes are converted to a program, executed, and their fitness is ranked according to the output of each program. So the closer a generated program comes to solving a particular task, the more likely it is to continue to the next generation. At each generation epoch, we use evolutionary techniques of roulette selection, crossover, and mutation to create child programs that are slightly different and hopefully better than their parents. So how do we construct a genome? So here's an example. This is a little bit easier to understand. Here's an actual example of constructing a genome from an array of floating point values. So notice how each floating point value maps to a specific instruction in the programming language. So you can see here how 0.6 is mapped specifically to the plus programming instruction. You can see there are actually 2 of them in this genome. Likewise, let's see here, 0.7 maps to a comma instruction, which actually corresponds to an input command. Now, initially, these floating point values are all random. They're just randomly generated. And so the resulting programs that get generated from these will be completely random. Because of this, they will most likely crash and fail with errors immediately upon executing, if they even execute or compile at all. However, 1 or 2 of these are bound to compile and bound to do at least something. Perhaps they increment a value in memory. Perhaps they output a character on the screen. They'll do at least something. And it's those programs that will move on to future generations to produce child programs of their own that are slightly different and slightly better than their parents over time. At each generation, we apply the, we take 2 parents to produce an offspring program in order to create the next generation of children. So we do this by taking the evolutionary techniques of roulette selection, crossover mutation. So you can see an example here of roulette selection. So we've taken 1 parent, which is at the top. The first 5 instructions come from the first parent. The next 5 instructions come from the second parent, and this forms 10 instructions, 10 genes to form the genome of a child. So you can see how in the red box, we're inheriting the first 5 instructions down into the child program. The child program is then inheriting another 5 instructions from a different parent. We also apply concepts of mutation. So mutation has the effect of slightly altering randomly one of the genes in a child program. So here you can see an example of how mutation was selected on the 3rd gene from the right, and it slightly changed the value of the underlying floating point value from 0.9 to 0.8. This has the corresponding effect of changing that programming instruction from an upshift instruction to a downshift instruction. Now, this may end up making the child program better or worse than the other programs that it used to behave like. If this program ends up performing better, it will have a higher fitness score, and thus it will have a distinct advantage over all the other child programs in its epoch, and it itself will move on to produce child programs that are slightly better and get better over time with future generations. After each generation, each program is ranked according to its fitness and according to how close it comes to solving the problem that it was asked to achieve. You can see in this slide how the top program fails and is eliminated from future generations. However, the bottom program succeeds and is carried forward to produce new offspring of its own. So why did the top program fail? Well, if we take a look at it, the first instruction is an input command, the comma. There's nothing wrong there. The second instruction, however, is a terminate loop command. Now, because we haven't even started a loop, this will end up causing an exception and will cause an error in the program and cause it to crash and fail. Now, since the program hasn't even produced any output, it's displayed nothing on the screen, it hasn't performed any calculations or performed any storage of values beyond the initial input, it will have a very, very low fitness score, if any score at all, and thus it will be eliminated from the gene pool. However, the second program is actually a valid executing program. It takes input from the user and prints those 2 characters as output as a result. Because this program actually performs something and outputs a result, it will have a higher fitness score and will move on to produce child programs of its own that get better over time. So what everyone's been waiting for is probably, what has the AI actually produced? What has it actually achieved? Well, the AI has been able to write programs that can produce output for hello world, It can perform addition, subtraction, multiplication. It can reverse an input string. It can take input from the user. It's even produced a program that can take two starting numeric input values and output the Fibonacci sequence from those two starting values. So it's produced a range of programs that are really quite incredible. And I want to show you an example of screenshots of a couple of these programs so you can take a look at what it's done. This is one of the earliest examples of the AI. The AI was asked to produce a program that outputs the word hi, just H-I. So you can see here how the AI has indeed produced a program. The output is right there with the arrow pointing at it. It's written a program that's outputting the words H-I, the letters H-I for the word hi, followed by a bunch of random characters that don't mean anything. This program was generated in 1 minute. So in just 60 seconds, the AI was able to learn a completely new programming language and write a program that outputs the word hi. Could you learn a new programming language in just 60 seconds that outputs the word hi? I would be surprised. It's quite difficult, but the AI did this in just 1 minute. Now, this is also an example of being careful what you ask the AI to do, because it just might do it, as it did indeed produce the word hi, and it wasn't told what to do after that. So it doesn't matter that it output a bunch of random characters afterwards, as long as it achieved its goal. So let's take a look at a second example. So here you can see the AI was asked to produce a program that outputs the word hello. It generated this program in 29 minutes, just 29 minutes. Again, it did produce a bunch of garbage characters afterwards, followed by a Stack Overflow operation. And this is actually quite interesting, as the AI was actually trying to optimize its execution time to terminate the program. And it output the word hello, which was its goal. And in order to terminate the program, it caused a Stack Overflow exception, which to the AI was a valid way to terminate the program. While we programmers look at an exception as a bad thing, to the AI, it was not considered a bad thing. It was simply considered a way to terminate the program. So I like to compare this idea to creating a robot that cooks you eggs in the morning, and it indeed produces you breakfast, followed by spinning around in a circle and then exploding in your kitchen. Now, of course, you don't want the robot to explode in your kitchen. You just want those eggs for breakfast. However, you didn't tell the AI specifically what to do. All you said was, make me eggs, write a program that outputs hello. And so that's what the AI does exactly. And you have to tell it what to do after that, or you might have unintended consequences. So again, be careful what you ask the AI to do, because you just might get it. But quite incredible result in just 29 minutes. Here's a much more advanced version of the program. It was asked, the AI was asked to produce a program that could take an input string from the user and then output the word hello concatenated by that input string. So here you can see I've typed in my name, Kory, and the AI's output the sentence hello followed by Kory. You could type in any text and it will indeed output hello followed by the text. So the program you can see is outlined in yellow. It's quite incredible. It produced this in just 30 minutes. 30 minutes, the AI is able to take input from the user, concatenate it to a string, and output both strings together in just 30 minutes. Also see that there's no more garbage output. The AI was able to clean up that issue through its training data and to come up with this clean, concise program in just 30 minutes. Here's another example. The AI was asked to produce a program that would output the sentence, I love all humans. The AI produced this program in 10 hours. Now, this isn't quite the modern version. The modern version of the AI can produce a sentence like this in a matter of minutes. But this version took 10 hours. You can see the program right there. The actual sentence is somehow encoded in that program in order to produce the output result. It's quite incredible it was able to do this. I just want to show everyone a couple of close-ups of some programs. Before that, let me show you, here's one of the most advanced programs that it's produced. The AI was asked to produce a program that outputs bottles of beer on the wall. This is a popular camping song that's often sung at campfires. So the AI was asked to make a program that will take a starting numeric input value, and it will then count down from that value to 0, outputting the numeric value, followed by the word bottles of beer, the sentence bottles of beer on the wall, counting all the way down to 0. You can see in the first example, the user typed 5, and the AI output 5 bottles of beer on the wall, 4 bottles of beer on the wall, 3 bottles of beer on the wall, all the way down to 0. It actually ended up printing out 255 at the end before terminating, because 255 is the max value for a byte, which is what the AI is working with for its memory. So there's actually a lot going on here. The AI had to learn how to figure out these programming constructs of taking numeric input, concatenating text to a numeric input, doing a conditional in order to count down and terminate in the loop, doing looping, as well as subtraction. So all these concepts come together in this program, which is quite a lot for an AI to produce. And it did this in just about 30 minutes, 33 minutes to be exact. I was quite surprised when it was able to achieve this, and it's really an amazing output. So here's some close-ups of some of the programs it's produced. Here's an example of hello. This was produced in just 29 minutes. This is addition. This will actually take 2 numeric input values from the user, add them together, and output the result. This was generated in 45 minutes. It's quite hard to believe that this program performs addition, but it actually does. Just 45 minutes this is produced. This is the Fibonacci sequence. This program will take 2 input values from the user and then output the Fibonacci sequence as a result. This program was produced in 7 hours. Now this program, the instructions in this program look a little bit different than the other ones that you've seen. That's because this is a more recent version, a modified version of the programming language that was customized specifically for optimal execution with genetic algorithms and evolutionary techniques. Some of these instructions aid the programming instruction set in order to execute more advanced features such as automatic shifting of address space values, as well as storage and retrieval, and quick setting of values. And it's able to evolve programs much quicker, such as the Fibonacci program that you can see here. So it's quite incredible how the AI was able to produce all these different programs and more in such a short amount of time. There's certainly a lot of potential in what could be done. I've been writing software for many years, and I've always felt that it's just something that humans shouldn't be doing. Humans should be designing the programs. Computers should be writing the code. So consider a future where humans create building blocks of program designs. The humans create these building blocks. They give these designs to the computer to actually implement. So the computer then actually creates these blocks as real software. The humans then design more complex problems using these original building blocks. The computer can then take those building blocks, put them together similar to the programming instructions, and create even more complex programs and larger solutions, creating applications and solutions for web applications, databases, games, and so much more. Just to show everyone, does this actually work? Is this actually a real thing? I always like to include a recent example in the presentation. And you can see here, I've asked the AI to produce a program that can output thanks 2021 TEQnation. And this program was produced in just 35 minutes quite recently. And with that, that's concludes my presentation. I'm a huge fan of artificial intelligence. I love talking about these topics, not just evolutionary computation with genetic algorithms, but also machine learning, data science, cellular automata, symbolic AI, and all the different areas of artificial intelligence. I'm very passionate about the topic. Feel free to get in touch with me. Reach out. My website is primaryobjects.com. Connect with me on LinkedIn and Twitter. And with that, I am open to questions and comments, and thank you very much.